Good afternoon. My name is Akka, and I'm an architect at PayPal. I have been working on the project now called Skills for about 4 years. And I think we have enough kind of traction to say it is well in production, but the first job that I had is how do we make this technology, this amazing technology, run Akka? And at that point in time, we are not even talking about Akka streams. How can we make it work in operations, okay, in production applications? So let me just ask a question here. How many people in this room code on Akka streams? We see about 20%, I would say. How many have not used Akka streams at all and don't understand what it is? Okay, so let me go over why we are doing Akka streams altogether. So the Akka actor model has got this amazing thing called the dispatcher. And the dispatcher basically tries to streamline your work from old architectures which might have hundreds of threads down to pretty much in the ideal case, the hardware CPUs, right? And there were Akka actors. They have got very good use. The previous session talked a lot about Akka actors. So I'm not going to go into that in much detail. We work on Akka actors still. But we also see a lot of future in streams. So the Akka streams is a reactive stream, or basically the Akka guys started the work on a reactive stream spec. So it definitely conforms with the reactive streams. And it has got some of these very good features. One is it's pure async, very high performing. Okay, it has back pressure, which gives you the resilience in most cases. I'll also talk about cases where back pressure is not enough, by the way, just a little later, all right? It gives you a great DSL, and for Scala folks, it would be almost perfect. You can see the picture of the whole app in one screenshot, I would say. For Java, a little harder. It's just a limitation of the language, but I wouldn't say it's second grade. It's as good as you can get the API in Java. All right? These unifying constructs allow us to understand every single application, everything that it does in just glancing at it. And if you have to read a lot of code like me, that's the first thing I'm looking at, right? The other thing that I want to talk about is we actually help, I'm part of the infrastructure team, which helps use cases go live. So I'm not going to talk about a single project. There are many projects that are using this infrastructure based on Akka and Akka streams, and I'll just take the tidbits from the end issues that we have learned on different products, on different services that are live at this point. So what am I going to talk about? The first thing is operationalization. What are the components that we are looking at? The first thing is lifecycle, okay? Pipelines. Pipelines is something that says, before a request or a message comes to your business logic, these are the standard things that it has to do. Before it leaves your business logic, these are the standard things that it has to do. Gates is a pretty new concept. We just coined that concept, basically, but I'm not sure it's anything new to Akka folks, okay? We will go into monitoring. Very important, you have to be able to monitor it. And at last, we'll talk about, yes, all of this is open source. And all of what I'm talking about is nothing secret. The code is right in front of you if you go to GitHub, right? So, what does it mean to do production at scale? And it just looks like that picture that you see, the truck carrying a load that it's not supposed to carry. And it can top over in any direction at any point in time. That's what it is, right? So when we look at operationalizing a service, you have to know that it's not one service. It is not one service with one architecture. For a company this old, and I'm not considering PayPal that old, we have got legacy systems that are 20 years old, 15 years old. We have got systems that are 5 years old, and we have got probably the newest generation of asynchronous systems. And perhaps a different breed of those coming together as well. So we are not alone, right? They will have to work together. They have to be monitored together. We are lucky enough, while we are doing DevOps, we also have central ops that keeps like a war room that looks at things going wrong at any point in time. So whatever we do has to plug into that. If something goes wrong, they have to be able to see it, right? And for that to happen, these three things have to come together. You have to manage the lifecycle of every service instance. And usually when we talk about services, a service might be multiple virtual machines, multiple JVMs, okay? In most cases, there's no service, let's say it this way. There's no service that we have that is on a single JVM, okay? So we have to monitor the lifecycle. We have to make sure that it can be managed. Logging is done properly, monitoring is done properly, tracing is done properly, and especially in the generation of Akka streams, that if things go wrong, it stays resilient. The bigger framework, Akka streams, end-to-end resiliency, gives us the promise of being resilient, but we cannot destroy that. If we do it the wrong way, and one of my first use cases actually did exactly that. They put two streams together with an actor in the middle. Now, the actor will bloat because there is an unbounded buffer. Or there's a buffer that is bounded, but you drop messages if you are hitting that bounds, okay? So let's jump into a little bit of lifecycle management. What are the requirements? The requirements are really, you need to know when a service, you need to know internally as well as externally, when a service is coming up, when it's ready to take your traffic, okay? And then when it's being shut down, and what to do when it's being shut down. I think that's the hardest part, is shutting down a service properly, okay? And we have to manage that without data loss. There might be arguments for and against it. We can take that offline, or I'll also address it again a little later, okay? Manageability requirements. I'm not going to read the screen to you. You can look down, and we'll come back to it many times. The first one is logging. Everyone has got their standard logging mechanisms, right? Then we are talking about, how many hits is my service taking? How long did each hit take, right? So we need to have all of that in place. We need to be able to correlate a message coming from somewhere else, I don't know where, coming to us. Where did it come from? How did it even enter PayPal? Or did it enter PayPal, or was it generated internally? We have to know all of that, right? The rest is just common, I think. So let's flip right to the next piece, which is resiliency. We talked about end-to-end back pressure. We talked about putting a stream that has the input and the output bounds on both sides. That helps you. But in some cases, you have to deal with not only back pressure. Back pressure is just saying, stop, don't send me anything because I cannot handle more load. Because my downstream cannot handle more load, my upstream cannot handle more load. So we have to be able to time out the downstream, okay, or retry the downstream, or basically use concepts like circuit breaker, okay? So let me start with an app that I just threw together. So this is just how it looks like. This is meaning nothing. There's nothing in production that looks exactly like this, but a lot of them look close, right? Where we have got a request coming in, going through multiple stages, and then at the end of it, you will see that there is a gateway going out, in this case an HTTP client, right? So this is an end-to-end stream. Seems resilient, everything is great, fine, you put it together, you throw it into production, and it should work. No, it doesn't. No, it doesn't. This is just the business concerns. But there's a lot of infrastructure concerns, right, that we have to take care of. So we justify the end-to-end stream, right? But I'm saying it's not enough. Let's take a look at what you have to do in the stream. And I think the first part is the lifecycle. Coming back to lifecycle, we implemented 4 lifecycle stages. When you start up the VM, or the JVM, you are going into a starting phase, or starting state. When everything is nicely initialized, and you start to take traffic, or you are able to take traffic, it's in the active state. When you signal it, or somebody signals it that I have to take you down, it goes into a stopping state. The stopping state is the most tricky state, by the way. And then once everything is down and you can shut down power, it's when it's in stopped state, right? There are many things that are depending on this. One is if you are great reactive infrastructure behind it, where you can back pressure up and everything understands it, that's great. But if you have a load balancer, the load balancer currently doesn't quite understand back pressure that well. It understands ECV, okay, or extended content verification, where it pings us on it pings the service on a certain URL, and it expects something back saying, I'm ready to take traffic. And if it doesn't get that, then it will not send traffic to you. So the active, or this transition to the active state, will have to enable ECV. There is something else. If you have a stream that will live forever, something that reads from Kafka, writes to ActiveMQ, or writes to Kafka, whatever, right? And it just keeps going. We call that concept a perpetual stream. It's not something that you create and you destroy. It lives for the life cycle of the service. And that's called perpetual stream. It's just basically a trait in Scala. And in Java, it's an abstract superclass, right? So it provides all the services to assemble a stream and bind it to the lifecycle, so that when it goes active, the stream starts fetching or getting traffic. When a stopping signal comes, it turns off the traffic on the stream. Okay, so but it's not done processing. Remember, everything is async here. You don't know when it's done processing. So it lets everything go down, trickle, and it monitors that you are actually done processing. Only then it comes back and say, I'm done. You can go to stopping mode, right? And that's why I said stopping is the hard part. If I chop it down right there, you will have data loss. And there are arguments here about, okay, idempotency, I can rerun the data. You don't have to commit to Kafka. Those are special cases. But in general, we try to minimize that. And that's why we are building this facility to make sure that your service lifecycle is fully managed. Okay? Next interesting part is the pipeline. The pipeline is, okay, if I use the term BD flow in this room, can you please raise your hands who understands BD flow? That's even less. Okay, good. So let me just talk a little bit about BD flow, because a lot of what we are talking about has BD flow as the main protagonist. So a BD flow, similar to a flow which goes one way, is actually a flow that goes two ways, right? You have traffic going, let's say, outwards. I don't know which one is left and right for you, but outwards and back inwards, okay? And we use that for many cases. You'll see in pictures. These BD flows are stacked together, and there's an operation in Akka streams called a top, which allows you to put one BD flow against the other and say, here is my set of flows. We can manage that from the infrastructure, and that allows applications that go live in your organization to have your pipeline, to have your logging, your tracing, your monitoring, okay? And the construct is just basically a standard Akka stream construct called BD flow, or bidirectional flow. So the last part is, by doing so, by using primitive constructs of Akka streams to put it together, Akka streams has an optimization called fusing, which basically fuses the whole flow together and minimizes the amount of asynchronous boundaries that you jump across. All right? So this fusing actually has reduced latency tremendously, in my experience. We have got some prototypes done with actors, and similarly with Akka streams. And at that point in time, fusing was very new. And we see the latency of data going through the stream, in case of HTTP, drop in half. Okay. So let's take a look at the pipeline. From the previous picture that you saw, which has got like the unmarshal, this, hopefully I can use this. Okay, Do you see that? Okay, good. So unmarshal is the first step. This is part of the business logic. So the pipeline is inserted into the system by our bootstrapping in front of it, where you can define, or infrastructure team can define the logging component, the monitoring component, so it can log on the way in, on the way out, monitor on the way in, the way out, latency that you use, okay? Security, the nice thing about BDFlow is you can short circuit it. So if security says, nope, I don't want to run, let this request through, it goes right back out. It doesn't even touch the business logic, all right? So that allows you to assemble these components together. And when you see, when I say at top, it's basically this kind of assembly. If you look at the aggregate of the BD flows together, it's also a BD flow. It's the same shape, right? It has got one input, one output, second input, second output. And protocol handlers are it's very useful for protocol handlers to be stacked together that way. On the client side, we saw that we go to the HTTP client. So we take our favorite Akka HTTP client, and we build something around it that says, now you use something, you use it exactly like the Akka HTTP client, but it's a different class. It's called client flow. And building a client flow builds a pipeline. That pipeline is also built following the spec that the infrastructure team has given you. Now, as an application, you might opt out. You might say, oh no, I don't need authentication. There is nothing here, right? You can do so. So we can provide multiple pipelines, or we can provide a pipeline that you can override and take in, take out components, okay, as you wish, actually. So generally, it's an infrastructure concern, but in some cases, it becomes an application concern. So we expose this API to the application as well. Pipeline components, I barely have to read this. This is all obvious to you that you need all these features in order to get a service or a messaging component, whatever, live, right? So now I'm going to change subjects altogether and go to stage gates. So what is a gate? A gate is actually a component. It's also a BD flow, by the way, so that's why I say BD flow is the main protagonist for today. It separates one part of the flow from the other part of the flow and allows you to monitor what's going on between that one part and another part. And it's not separating in two. In real cases, real use cases, we have got multiple separations, right? This is what we do resiliency with in most cases, beyond what we deal with back pressure. So here's how it looks like. So we have got the main flow, and you might have, in the gated flow, you might have access to another service, you might have access to the database, some external resource that could be down, right? So how do you deal with that in a streaming environment? We put a gate in between and say, this is the main one, this is the high-risk one. And if the high risk goes away, we have ways to deal with it, right? For instance, the circuit breaker, which is one of the standard components that we provide, actually is performing exactly this function, right? Where it allows traffic to pass, but if you error out too much or you time out too much, it will stop. And it will short circuit that flow and say, I'm sorry, that component down there says it's not available. Let's leave it alone for another few minutes, and we'll come back, okay, and see whether it works. So the main flow can decide to do whatever it wants to do. The error messages or the replacement content that you might get out of the circuit breaker is absolutely customizable. And usually, we can customize the minimum, and you can put another flow component that expands it into whatever response you want to get out of it. So, common gates. The first part is probably a timeout. And a timeout is actually short-circuiting backwards, right? So whenever a request that goes down to this high-risk flow doesn't come back on time, it sends an error message back saying, this one timed out. When that other response eventually arrives, it may or may not arrive at all. If it arrives, we say, we discard that, we send a timeout. So there's some identification that has to happen to know which message is which message, because everything is a message flowing down and flowing back up. A retry is short-circuited the other way. I send something down and I get a response back. And I'm not happy with the response. Okay, so not happy doesn't mean that it has to be an error. It could be anything. You can put in what you want to classify as not happy. And if I'm not happy, I'm going to retry it. The current version has static retry intervals. The upcoming version that we are putting out will have a exponential back-off retry as well. Okay, circuit breaker, we talked about that enough. Looks like a timeout. When it breaks the circuit, when the circuit breaker is open circuit, then it will just send a message back that says circuit breaker is open, right? And that is well typed, so you can put another string component behind that and say, what should I do when it's open? You can translate that, right? And then common monitors. I want to know something about that other part of the flow. So I have got counters, okay, that go in and out. I measure the latency not only from front to end, but in this part of the flow. So you'll see that that picture that I had before is just showing one gated flow. In the real-world applications, we are dealing with multiple gated flows, right? All of these components that we provide do have stats. So they expose their stats through JMX beans. They log Codahale metrics, right? So feel free to adapt it to whatever you need to. State sharing. Okay, this is getting interesting. So if you are not familiar with Akka HTTP and Akka streams, let me go back one step and say, for every connection coming in for Akka HTTP, you are materializing a separate flow, right? So which means that if I've got 100 connections, I have 100 instances of the stream running. If I am circuit breaking something going to full service, then it should be broken. The circuit should be open for all streams. In some other cases, you might have some other streams that come through other parts that also access full service, which have a totally different topology. And only the application developer knows that, in fact, you are talking to the same full service here. So the circuit breaker, in that case, will have to have a state that you can pass around. So that is the beginning of what we call circuit breaker state. And the same thing can happen for timeout state and so forth. Any gated flow can have a state that is explicit to itself. Not that you have to look into what that state is. It exposes it through JMX. At least what we build exposes it through JMX for sure. But it allows the application developer to take that state and pass it to multiple parts of the flow and say, guys, this should be counted as the same resource, right? That is one design around this multiple flows and that shared external resource. So this is a second big piece of the operationalization. Let me context switch now to monitoring. Okay, and Akka HTTP, Kafka, whatever we are doing, that we have plenty of those input modes. We don't only do HTTP, by the way. We do all of the above, right? We have to monitor all of them, right? So what do we need to monitor? We need to know the request rate. How many requests are coming in per second? How many open connections do we have? Now, as I told you, in Akka HTTP especially, an open connection is a stream. So it will tell us how many streams we have active. New connection rate. Okay, so some of them, even though we prefer persistent connections, there's this little a little HTTP header that says connection closed. And that means that if you get that header, we have to close the connection. And there are some clients that don't like open connections, so they keep closing the connection. If we serve a multitude of clients, we are facing this issue. We don't know how many connections are being created at any point in time. So we need to monitor that. And that is basically the materialization rate. If the materialization is extremely high, if we are taking 40,000 hits And all of them are resulting in new materialization. I know that Akka can handle it, but it's going to be pretty heavy. So materialization will be a major workload for you that you have to look at. Okay. We need to look at in-flight requests, requests that are coming in and not going out yet. We need to look at streams. Streams can collapse. If you have errors and the errors are not handled, they can collapse. And you can assign a decider, which is a global error handler, onto that. But we want to know when streams collapse and know that some of these requests that come in never got responded to. Okay, it may be an error condition. It may not be an error condition, by the way. We need to monitor, in some cases, HTTP response codes, especially for HTTP. You need to know how many 2xx you passed out, how many 3xx you passed out, and how many 5xx, 4xx, you know. So those are monitors that come into play. And besides that, of course, this is not part of the offering. Let me just be very clear, but we do it internally, and it might be depending on the OS you are using, versions you are using. You might be able to get that in different manners. So that's the systems and network statistics that you should get anyway, right? There's a special case that I just had the pleasure and the joy to put live, okay? And it has been a pain, by the way. So this note of saying be tolerant with others and be strict with yourself is coming in very handy here, because Akka HTTP, at least I'm sure some of the guys that have done Akka HTTP or even developed Akka HTTP in this room, so I would say it's not the most tolerant. Okay, and if you use the routing API, it's even stricter. It wants you to conform to HTTP standards. But when we go out beyond our firewalls, it's a Wild West. Somebody is shooting something at us that we don't understand, right? And we need to understand what that traffic is. You create a service that is externally facing. You have got an API spec nicely published out there, but people call it, and they have got some extra headers, for instance, and they expect something back. A common one that I ran into is accept and text HTML without a star in the back. So it only accepts text HTML. But that service, for some odd reason, always returns a GIF. So the caller should never put such a header in. Should we penalize them? No, right? So for that, we built a couple of things. One is what we call a request sanitizer. That's also a pipeline component that looks at the requests and say, what is really invalid in this request? We try to serve as much external requests and reject as few external requests as we can, right? So we have to look at them before passing to Akka routing, Akka HTTP routing API. We have to say, okay, these are the things that are not supposed to be in the call. Take it out. Otherwise, it will be an error. And we also, at least when we bring it live, we have to put in a request logger, which means that if we sanitize and for some odd reason we can still not handle that request, we have to log and tell the team, hey, here are sample requests. So if your request rate is very high, you might want to sample it. Or if your error rate especially is very high, you might want to sample it. If it's not very high, you just log every one of them and let the team look at every one of these requests and say, what's wrong with this request? Can I go to the internet and tell every one of our clients, hey, change your request format? That's not going to work, right? So we just have to swallow that. All right. The last part is talking a bit about the offering on Skills and what it's not, what it is. So let's start it. What's it not? People would yell out, oh, you are building me another framework. No, we are not, okay? We are not even trying to tell you any APIs. We have a very minimalistic API. I call Skills has two parts. One is the bootstrapper. The bootstrapper is basically dealing with the lifecycle I talked about and dealing with installing the pipelines and everything on the HTTP side. And there is the component parts, which are the gates, the circuit breakers, and all those. We'll talk a little bit more about those. Okay, but it's not a framework. It has got these two main components. It has got a module system as well, and it's not all or nothing. If you want to use anything out of skills, you can use one component, which might be 5% or 2% of skills. You might want to use the whole lifecycle management, which might get you to 50% of skills, and you might want to use both, which gets you to 100%. It's not all or nothing. You are not locked in, and it's not my job to lock you in here. Okay? What we do is exactly what we say. Bootstrapping, lifecycle management, module system. I have nothing else talking about the module system, so let me spend a minute here. The module system is very useful when you have multiple services that interact with others. You might want to test them together. Instead of spawning 5 JVMs for 5 services, you might want to group them together and put them in the same module, talking to each other through HTTP, through messaging, through many ways. Okay? We also use it in production for some of the components that are required. For instance, admin consoles that you want to see how the system is doing. You don't want applications to say, go write code, install this admin console in your code. No. We basically take care of that. You just drop the admin console in, and we provide one for open source as well. And you could see the internals of the system, right? And of course, the hooks that we talked about already. So the console is a JSON console. Okay, you can integrate it with about anything. We try to pretty print our JSON for this purpose, but it's for human consumption as well as for machine consumption, basically. There's a resolver concept that allows you to run with different resolver mechanisms in production versus in QA versus in dev, and that's very much needed for large enterprise applications. And beyond that, it's test tools, interfaces, goodies, programming patterns, templates. All of that comes together. When you start using it, you can say, OK, I want to start doing my basic skills project. You'll get it on your workspace within 2 minutes, basically. All right? So make it easy. Next part is Alpaca. So everything we do that can be open source as independent components are posted on Alpaca. And Alpaca is the Akka. So this is like an animal that looks like a camel, reflecting Apache camel. And the Akka team has put this together to create integration points for Akka streams. And they have got a pretty rich set of integration points. So we are writing on that. We are proposing component models. I think integration, there's a lot there already, but components, there's too few. So what you see listed here is what we have currently. Let me also spend 1 minute talking about one special piece here that I haven't had a chance to talk about, and especially in the resiliency side. So in some cases, you can back pressure. Akka HTTP has this nice mechanism to push back on service calls that says, I cannot handle your load anymore. But in some other cases, the other side doesn't honor that. So you have to gulp in whatever is given to you. And for that, you would rather put it into a buffer and say, well, the downstream is not ready to handle it yet, but I want to buffer it up. But you have got your, whatever, 4 gigabyte heap in the JVM. If you really go for big heaps, 16 gigabytes, that's pretty big. Okay, or other VMs might support even bigger heaps. So that is not adequate. So we have got those use cases where we say, we cannot say no. We have to get everything in. And therefore, we have got a memory map buffer, which actually uses a file underneath. It writes to local disk. So it is durable to a certain level. And normally, in normal operations, that buffer should be empty. However, when the downstream says, I cannot handle load, Kafka downstream, for instance, says, oops, I'm rebalancing. Give me 30 seconds to rebalance. You can put this in the buffer without bloating your memory. Okay. So this comes in handy if you just have no way to deny and you still have to gulp it as much as possible. There is a flaw, and instead of telling you or letting you pointing it out, let me just do it right now. These are local to the VM or to the systems that you are using. So before it gets more persistent, more durable in Kafka in the back, each VM is persisting to local disk. If you lose that VM and you bring it back up, nothing is lost. But if you lose that VM for good, then you have data loss. But that's a risk that you have to incur in the assumption that the backend system might not be available for you. You might want to find other ways to keep the data in two places. For instance, the cost is increasing, the durability is increasing as well. So based on your requirements, you can do all of that, right? So with that, let me step to where we are heading. All right. 1.0 is on the horizon. We are thinking, I'm not going to commit to dates, but we are thinking sometime early next year we should be able to release a 1.0 version. We have been in 0.x for 4 years, so it has been used in production, pretty mature. Okay, and only reason we don't go to 1.0 is we take versioning, semantic versioning very seriously. When we say 1.0, it means the API will stick. Okay, I'm not going to change anything anymore. So the 1.0 will be based on Akka 2.5 and Scala 2.12. The Akka APIs will be, probably for the whole 1.x train will be 2.5, and we'll have to move a major version if the Akka API changes, right? Actually, we have got a 0.10 in line already, which is basically we can call it 1.0 M1, okay, which is coming out sooner than that, allowing us to make some final adjustments before we declare a final 1.0. We want to make sure the APIs, all the documentation, we have pretty good documentation, I believe, but making sure we have no gaps in the documentation. Okay. More components, more goodies, as we learn more, as there are more requirements inside PayPal and outside PayPal, we are going to build these components. Anything that we can make open source will be open source. We are not going to hold anything back here, all right? Monitoring, in the last couple of weeks, I've learned much more about monitoring already, especially in case where things don't go as good as we wanted it to go. I get error rates, unknown error rates from Akamai, for instance. That's the external service we are talking about, right? And what does it mean beyond 1.0? So distributed, I mean, Akka has been supporting distributed and distributed patterns, distributed deployment for a long time. We are, I would admit, a little bit behind on that, and there are many use cases that need it. Okay, so the whole distributed scenario, the big data pipeline, talking to Spark, Flink, and others, and including some other new ideas that come up which allow our operations to be more resilient, our networks to be more resilient, I think are going to be very useful addition beyond Skips 1.0. Okay, so you'll have a rock-solid platform with 1.0, and after that, basically, we will go into experimentation mode and do the best to make sure your Akka cluster combined with whatever else, Kafka, Spark, all of that will come together and will all be operational. And operational not by my sense, but by your sense, by the way. And that's it. To summarize, of course, why we go to Akka Stream once again, high throughput, resiliency, visibility, all right? And operationalization is our job. It's why we started this project. We are not just saying, oh, this is a cool library, let's pull it in. And Akka is not only a library, it's a framework as well. It's a way of programming, which is very different from if any of you are Spring programmers. Even if you do Java, and trust me, the Java API on Akka is as good as it can get. It will, from language limitations, never be as sleek as the Scala API, but that's what the Java community has decided, right? They want to be verbose. They want to make it very clear, very explicit about everything. Scala basically takes certain concerns and hides it away. And you can go either way. You won't go wrong either way, I would say. And the Skips API supports both Java and Scala, by the way. And anything that we do is very focused on performance. When we put together the pipeline architecture, we were very worried about how much are you going to pay for this? Are you going to take Akka, which is a lion, and make it a cat? I don't think we want to do that. We want to make sure it actually stays as performant as it can be, right? And we want to continue to provide you hooks into operationalization for any future technology that comes up in this reactive, mostly on the Akka stack, all right? Okay, that was my last slide. You can always join us on our chat room. Go to our site. You can take note of that. It's PayPal Scoops on GitHub. And then click on Join Chat. I'll be there. Our team will be there. And you can follow us on Twitter at Scoops, myself at @Akara. And trust me, I'm not going to tweet a lot. I'm much more in the trenches trying to get our systems live and well than tweeting, but you'll hear from me from time to time, all right? And with that, let me open, I think we have got about 10 minutes for questions. And if that's not enough, I'll be at the booth afterwards. So we have got a booth. Drop by, talk to us. I'd like to hear your feedback. Thank you. Any questions? Discussions, comments? Yes, where can I have the mic?
Hi, you mentioned that you didn't use actors anymore right now, or you still use it somewhere?
We use actors. So how, right? Streams are great. They are more defined than actors. The directions of the messages are well defined, and the protocol you are not firing and forgetting like an actor, right? So I would say the backbone of the application, new applications that we do are all streams, but there's state. Something has to hold state somewhere, right? And it could be local on your machine, or distributed on a different machine on the cluster. For that, there's actors. Okay, and there are certain other patterns that are not well defined. You don't know who you are communicating to. You spray messages across multiple components. Those are actor use cases. Okay, so yes, we support both.
So seems like your framework is like a request response based kind of framework, like where a request shouldn't go missing in any case, right?
Most of what I talked about today, yes. So I talked more about the use case of Akka HTTP, but we have got a whole bunch of Kafka use cases, which basically goes one way down the stream in general. But there are also Kafka use cases where you have got this turn in the stream where we have to get off yet another service call in the middle, right? So the Akka HTTP use case is the more complex one, and that's the one that I just pulled up today. All right, thanks. Anybody else? Back there.
On one of the slides you threw up, it seems like you're passing like a request context all the way through all of your stream processing. I was actually just curious, is that something that you guys build, or is that something that you are utilizing as part of Akka HTTP and Akka Streams?
No. The request context is something we built. It's actually a very thin structural type that will encapsulate both the request and response and certain attributes. And that's a little bit missing in the Akka HTTP side. If they had it, we would have used it, right?
Is that something that's passed across service boundaries as well?
Service boundaries, no, you have to pass it as metadata. So there is this tracing, and you can build pipeline handlers to translate your request context into metadata that goes across your request, or depending on what it is. If it's a Kafka message, there are fields that you can put into the Kafka message that declares the metadata. And for HTTP, it's just HTTP headers, right? That has to be done. We don't have that, but that's actually a good idea. Thank you. That's something we probably want to do. Anybody else? All right, in the back there.
Hi, just wanted to know, in terms of, say, any deployment strategy or any kind of a hooks that if we even considered that, and the number of, might be an integration level or something.
Yep.
The tests to do.
It could be a talk by itself, what you are asking. So we tend to have standards not only for Akka, but for all the services. We have deployment strategies that span across data centers. There are minimum requirements to say how many do we need to be resilient. And the common deployment strategy that we use, I can talk about ourselves, is stateless, which is basically you have no state sharing between a cluster, right? The next step of deployment strategy is how do we manage a cluster? And that goes into a different team, different organization that deals with the path layer. Okay, so I would rather I'll just leave it here, take it offline, and feel free to drop by our booth. I'll be there, and I can explain to you and see what your requirements are. Perhaps we can help share some notes there, right? Thank you. All right, if there's nobody else, or if you are too shy, come join me at the booth, all right? Thank you.